Hello and welcome to this EE514 lecture on a bit of review on linear systems and using state space equations to plot state trajectories. Where I'd like to start is the state evolution equation. So if we have a linear system, then it can be expressed as a set of n first-order differential equations. So what we're doing here is the standard assumption that the x vector is an Rn vector. And while these notes assume that the input is a scalar, actually everything holds true if U is m-dimensional as well. But since they are differential equations, they can be Laplaced. So in particular, if I take the Laplace of the left, it'll be equal to the Laplace of the right. And Laplace of a derivative is s times the Laplace transform minus the initial condition. And since Laplace is a linear operation, then Laplace of a times x of t is the a pops out, or you can factor out the constants from the Laplace transform. And what I'd like to do is I'd like to isolate x of s, so that is the vector of Laplace transforms of the state. And I'm going to move this guy over and this guy over here. And I can almost factor out the x of s, except that this is A is an n by n matrix, and s is a scalar. And so the trick here is to insert an n by n identity matrix, at which point you can write this line as si minus a times big X of s. And then we can invert this matrix and left multiply both sides, and we get this expression for the state in terms of the initial condition as well as the forcing function. So just to remind us where this all comes from, or another way that you've seen this, this would be what one would call the zero input response, or the zero input state evolution, and this would be the zero state response, or the evolution of the state assuming zero initial conditions. So if we take that zero input response, then, so sorry about the order here, but I'm going to start with this expression and we'll work our way back there. If we're taking the zero input response, then the Laplace of u will be 0, which means that I'm only left with this part of this expression. And now if I inverse Laplace transform both sides, then I get x of t on the left, this vector x of t, which describes what we call the trajectory of the state. And on the right, I get the inverse Laplace transform of this product. Now, x of 0 is a constant, so just like before, we can factor it out or pull it out of the inverse Laplace transform, which is also a linear operation. And so what we get is that the state at any given time is equal to a function times x of 0. So this is actually, well, this is going to be an n by n matrix of time functions. Now what those are we don't exactly know, but the good news is that it's a matrix operation, it's a linear operation. So in fact what is commonly done is this inverse Laplace of an si minus a inverse is given the symbol big phi of t. That's called your state transition matrix. And it's simply defined as the inverse Laplace transform of si minus a inverse. Okay, so what we've just shown is that the state at any given time, if we knew it, we could take the state transition matrix and multiply it by our initial state, and we would get the state at any given time. The big question that I had when I took this class is, well, what is this thing? If I have A, I ought to be able to compute it, and it's very, very messy, right? Because there's an inverse here, there's also an inverse Laplace there. So this is, it's nice because we've shown that we can write it this way, but it's not particularly helpful because it doesn't tell us how to compute the state at any given time. So to do that, I want to actually rewind a bit and go back to the time domain. So again, we're going to do zero input, which means that the forcing function is going to be set to 0. And so here we've got this we'll call homogeneous expression, right? A bunch of first order expressions in which the derivatives of the functions are equal to linear combinations of those functions. And the inspiration we're going to take is from one-dimensional differential equations in which the homogeneous solution always took the form of e to the, at, that kind of deal. So what we're going to do is we're going to assume the solution has the form like this, that the solution at any given time to this diffie q is, again, a linear function of the initial state. Now, why this particular series? Well, we can again point to the inspiration from kind of regular one-dimensional diffie q's. If I have y prime of t plus a times y of t equals 0, then the solution to this will always take the form of the homogeneous solution, which is e to the minus at. And because this is an exponential, that means it follows the Taylor series expansion. So this is the same as, but the Taylor series expansion for an exponential is 1 plus minus at plus minus at squared over 2 factorial, etc., etc. And so what we're doing is we're taking inspiration from that, and we're saying, well, can we write the solution of this system of diffie q's in a similar format? So this, think Taylor series. And just because we say that that we think the solution is that doesn't mean that it has to be true. So let's go ahead and show that it's true. So if I differentiate both sides, then what we get is this guy differentiates to 0. This one we lose the t, and we knock down our powers of t, just like your regular differentiation of polynomials. And the observation now is that I can factor out an a out of all the remaining terms, and I am left with a times this thing, but this thing is exactly this assumed form at the very get-go. All right, so that is the proof that our assumption was accurate, and that the solution to this homogeneous system of differential equations is solved by this function. But if you'll notice, that means that we have two equivalent solutions, one that we got from the time domain, the other that we got from the Laplace domain, and they have to be the same. And so this is the big takeaway, and that is this box is equal to this box, which means that we finally have an expression for the state transition matrix. It has to be this parenthetical. So it's important enough to have a name. The state transition matrix for an LTS system is called the matrix exponential. And it's simply defined as the identity plus its argument squared over 2 factorial, etc., where the argument is a matrix. And it's important to differentiate, to tell the difference between a matrix exponential, where if I have e to the matrix, this is not the same as a matrix of e to the first element, and then e to the second element, etc. Okay, so this is, the matrix exponential is not a matrix of scalar exponentials. That's an important distinction to make. So whenever you see an e to a matrix, you should, at least in this class, perhaps there are other classes in which this is not true, you should think of this infinite Taylor series. There are a lot of nice properties that the matrix exponential has, including if you take e to the at transpose, well, that's just the same as e to the at transpose. And there are a lot of similar results you can do just by using the definition here. One thing that is not in general true is what I have down here, which is what you would want if this acted like a scalar exponential. And I say be careful because this is true sometimes. It's true when the two matrices commute, but it is not true in general, right? Because this is not true of matrices in general. So it's powerful, but you can only use it in the way that it should be used. And in Matlab, by the way, to get the matrix of scalar exponentials, you would use this. So this equals e to the m1, 1, etc., etc. Whereas expm is going to be I plus m squared over 2 factorial. Right? This is the matrix exponential in Matlab. The key takeaway so far is that if you want, for a zero input type situation in a linear system, if you want to compute the state at any given time, you need the state transition matrix at that time. What if you have a total response? So you have both a response due to initial conditions that are non-zero and a forcing function that is non-zero. Well, the matrix exponential actually helps with that as well. So we are now no longer assuming any of these terms are 0, but what we are going to do is we're going to left multiply both sides by this matrix exponential. And then I think what happens here is this just gets moved over to the other side of the equal sign. And then the key observation here is that when I take this derivative, so let's look at d dt of the product of these things. So this is an opportunity for product rule. So this is derivative of the first times the second. So d dt of e to the minus at, that thing times the second, plus the first, the matrix exponential, times the derivative of the second, which is the vector x dot. So we now need to figure out what is the derivative of the matrix exponential. So maybe we should write it out just to be sure. So e to the minus at is identity plus minus at plus minus at quantity squared over 2 factorial, etc., etc. So if I differentiate this, so take a d dt of both sides, the identity has no t's in it, so it becomes 0. The first order t drops away, and then we get something like minus a squared times t over 1 factorial. And then so that the powers here are going to knock the factorials down by 1. That's the idea. Plus dot dot dot. But what happens is that this is simply minus a times the original matrix exponential. Right? So that matches with that, that matches with that, in whatever direction you want to think about it. So one of the nice things about, and one of the reasons we call it a matrix exponential, is because it obeys the same differential or derivative rules that the scalar exponential does. So this allows us on the left-hand side to say this is minus a e to the minus at times x of t plus e to the minus at x dot. Why is that important? Well, we can match terms now. So this appears here, and minus e to the minus at times a times x, it almost looks like this, doesn't it? Almost. The problem is that the a is in the wrong place. And so this is one of the other nice things about matrix exponentials, is that the a can go on either side. So there's no reason that we had to multiply the negative a from the left. This is also e to the minus at times a from the right. Right? Because everything here is a squared, a third, and it doesn't matter. A times a to the n minus 1 is the same as a to the n minus 1 times a. Okay, so that's the trick. So this is actually not an almost. This is a check mark. So that does match up. And so that's why I replaced the two terms on the left-hand side with this derivative. And then what we're going to do is actually integrate both sides. So the other way to think about the matrix exponential is as an integrating factor, if you want to connect this to your differential equations classes. So if I integrate the left and I integrate the right from, say, 0 to little t, then fundamental theorem of calculus says I can evaluate this at the upper endpoint minus the lower endpoint, and e to the a0, well, that's going to be e to the 0 matrix, and e to the 0 matrix is just identity. All right, so last thing to do is to move this term to the right-hand side, and then multiply both sides on the left by e to the positive at. And because at and negative at commute, then we can use our property from the be careful property from before. And so these will eliminate each other, and we get an e to the at here and an e to the positive at here. And so we get an expression for the state of the system at any given time as the same ZIR that we had from before. So it's good that we recovered that, but also this term, which has nothing to do with the initial conditions. So this is, we might as well call that the ZSR. And I want this to make sense because this also, you can think of it as kind of having the form of the convolution, right? So if you squint, this also looks like a convolution integral as well. So let's try it out on an example. Let's take a classic RLC circuit. So the forcing function, or the input to the system, is a voltage source that varies with time, and we'll take the output as the voltage across the capacitor. We'll leave these as kind of generic RLC elements, and if we define the loop current in this orientation, then the common way to set up the state for this system is to let the capacitor voltage be one state element and the loop current be the other. And if you go out and you work the Kirchhoff's laws on this, you end up with an A matrix and a B matrix like this, and the output is simply the first state element, so that's why our C matrix looks like this. And of course a 0 capital D matrix. Okay, so what I'd like to do is I'd like to switch over to Matlab and show you how we can use the results that we've gotten so far. Okay, if we're going to numerically simulate this RLC circuit, we're going to need some numbers, and I picked the totally realistic numbers 1 ohm, 1 Henry, and 1 farad. Right. Set up the state matrices that we derived on the previous slide, well, that I told you on the previous slide. And let's see how we can use Matlab to help us plot the state trajectory over time. So I'm also just picking a kind of an arbitrary initial state. This is, let the capacitor start with 1 volt across it, and let's assume that the initial current is 1 amp counterclockwise. So one way to do this, and this is probably the easiest way, is to use Matlab's initial command. So initial takes a state space object and an initial state, and it ought to plot the result. So let's set this up real quick, and we'll just run these 2 lines. Okay, so doing this, we get the output of the system as a function of time. So this is valuable, but it's not actually what I wanted to show you. I wanted to show you how to get the trajectory of the state. So plotting in the phase plane, or the state space, where the system will go. And just observe that we start with 1 initial volt, and we start with a negative slope, which is the initial condition. And then the stable circuit eventually dissipates everything back to 0. All right, so to get to what I actually wanted to show you, I want to give the output. So this is the same command, right? I'm using the exact same thing, except I'm giving it some output arguments now. And these output arguments are y and t, which is what we're actually looking at here. But this third argument is where the money's at. That will tell you the state elements at any time in the t array. So if I run these lines, then we get the phase portrait of the system. So it's not actually evident just looking at the figure, but this is our initial state, right? 1 volt, comma, negative 1 amp. And then we can trace the state trajectory towards the origin, okay, as you would expect for a stable system. That's all well and good, but it actually doesn't use any of the things that I just taught you in this lecture. So in order to do that, let's implement the Matlab matrix exponential. So this has to be done, well, the way that I know how to do it, it's done in a loop, particularly because if you try to do A, the matrix, times T, an array of time values, the dimensions don't work. And so what you need to do is you need to scalarify, or do this for every time individually, which is why I've put it in a loop, which is I don't feel great about, but I actually don't know a better way to do it. And then what I'm doing is I'm just calling this a new variable name, and then we'll plot it against what we have just here. And there you go. Using the initial function in Matlab, we get the blue curve, which is now completely obscured by the orange curve, which is what we get using this matrix exponential. So they're the exact same. That's why you can't see two curves. So that's kind of cool that we learned basically how to replicate kind of a very black boxy type Matlab operation with the initial function. And also, I wanted to show how to model the full response, the total response. So I'm just going to pick a forcing function. This is a DC voltage along with a decaying exponential. And I'm going to use the same T array that we got out of here. So we'll come back and see if we need to make it finer or not. And I'm going to define my initial condition, same initial condition as before. And because there's an integral, I'm going to run a nested loop. And so to get the total response, for every time value, that's the outer k loop, I'm going to run the integral, which is a kind of a Riemann sum of the a times t minus tau times b times u. All right. So for any given time value, we're going to add the zero input response that we had before with the kind of zero state response that we'll get by integrating up to that time value. And what I want to do is I want to compare that with the other methods that you might know to solve this. One of which is called basically Matlab can integrate an ODE that you give it as long as you give it the functional value of that ODE. So here I'm defining the state evolution as ax plus b times u. And I'm using an anonymous function to do that because the EE514 Matlab command takes that anonymous function as its first argument. And then we give it a time span, so go from the first element of t to last, and also include this initial condition. And also, there's a third way to do it, perhaps you're more familiar with this, is that's using the lsim command. So this takes a state space object, it takes an array of forcing function values, and it takes an array of time values and an initial condition. So these are probably the top 3 ways to simulate the state trajectory of a linear system. So if I run this, cool, we get a pretty good agreement with 2 of the 3, and 1 is a little bit off. And I think that is mostly due to the kind of discretization factor. So the 2 that agree are the kind of more black boxy of the 2. They are the ODE method and the lsim method. And I think what we can do is, well, I mean, they all generally have the same shape. They all go to the steady state condition 1 volt, comma 0 amps, which is what you'd expect for a thing that eventually looks like a DC step. But if we force the time array to be a little bit finer, right, the issue that I'm looking at here is this kind of initial step is way too coarse. Right, this is a linear interpolation from this point to this point. And so if I force the time array to be finer, then I get a whole bunch of curves in here. So I got to close this and then plot it again. How about that? Okay, so I think I've made this a little bit finer. The downside by making this even finer is it's going to take longer to run because this is a nested for loop. Wait for it. Yeah, so already it's getting better. So this initial jump is getting less and less coarse. But because I'm doing kind of the naive thing, which is discretizing the time array in uniform chunks, which ODE45 and LSIM doesn't do, I'm paying the price because I'm getting both long run times as well as kind of an inaccurate result. But I think the essence of how these two methods could work for linear systems is encapsulated with this nested for loop topology. Cool. Thanks for listening, and I'll see you in class.